The singularity reconstructing a vanished epoch. What physics can and can't tell us about less than zero. When we talk about the beginning of the universe, we often imagine rolling back the cosmic clock, rewinding the galaxies, the stars, the atoms all the way down to the very first moment. This picture feels straightforward, like running a film in reverse. In physics, we even have equations that let us do something like that. General relativity, our best theory of gravity in space-time, allows us to take the current expansion of the universe and calculate backwards. We can shrink the size of the universe, going further and further into the past, getting a clearer picture of what things might have looked like just moments after the Big Bang. But there's a point where this breaks down, a wall we keep hitting. That wall is known as a singularity. To understand what that means, we have to start with what general relativity actually does. It describes how matter and energy curve space and how that curvature affects the motion of objects. According to Einstein's equations, if we plug in the current state of the universe, how it's expanding, what it contains, and how matter is spread out, we can predict what the past looked like. This works surprisingly well. It lets us rewind the universe all the way back to when it was less than a second old. But as we push further back, past a trillionth of a second, past even smaller slices of time, the numbers stop making sense. We reach a point where density and temperature shoot up toward infinity. Space becomes infinitely curved. The equations give outputs that don't describe anything real, just mathematical chaos. That's the singularity. It's a point where our current theories fail. In the case of the Big Bang, the singularity sits at time or t equals to 0. It's the barrier to knowing anything about earlier times. In simple terms, we can say that general relativity can't describe the universe at the exact beginning or before it because the math breaks down. The theory needs space-time to be smooth and continuous. But when the density of matter becomes infinite, space-time stops being smooth. It tears apart in a way. This tells us something deep about the nature of our understanding. It means there's a limit to what we can know by using general relativity on its own. No matter how good our measurements get, no matter how powerful our telescopes become, we can't rewind the cosmic movie past that point. Not with this tool. Now you might think, why not use quantum mechanics instead? After all, quantum physics is the other major pillar of modern science. It describes particles, energy, and the behavior of matter on the smallest scales. But quantum physics has its own limitations. Quantum field theory, the version of quantum mechanics that combines particles with fields, is built on a fixed spacetime background. It assumes space and time are already there, smooth and well-behaved. That works great in many situations, especially inside particle colliders or atoms. But it falls apart when space-time itself becomes wild and chaotic, like it does at the Big Bang. To really describe the beginning, you'd need a theory that combines both general relativity and quantum mechanics into one single framework. Something that can handle extreme density and high energy, but also deal with the warping and breakdown of space and time. That's what people mean when they talk about quantum gravity, a theory that doesn't yet exist in a complete tested form. Until we have that, we're stuck. Our current tools let us get close to the singularity, but not through it. This puts a hard boundary on any talk about t less than 0, aka the time before the Big Bang. In classical physics, time is a line, and we can trace it in both directions. But near the Big Bang, the classical picture of time no longer works. In practical terms, it means we can't say what, if anything, was happening before t equals to 0. Some models try to push the boundary by changing how we view the earliest moments. For example, some versions of cosmology start the clock not at t equals to 0, but at t equals to 10 to the power of minus 43 seconds, what's called the Planck time. This is the smallest meaningful unit of time in physics. Below this threshold, quantum effects and gravity are both so strong that we lose all predictive power. It's not just that we don't have the data. It's that the rules themselves might no longer apply. It's as if the entire concept of time stops being meaningful. From this angle, the past isn't hidden. It's undefined. The tools we use to define time and space don't work in that regime. When density and temperature go beyond certain limits, when energy levels become extreme enough, even the language of physics, mass, distance, time starts to fall apart. This isn't the only time singularities show up in physics. They also appear inside black holes. If a star collapses past a certain point, general relativity predicts a singularity forms at its center. An infinitely dense point surrounded by a boundary called the event horizon. Inside that region, time and space behave in ways we don't fully understand. And once again, general relativity fails at the singularity. This parallel hints at something deeper. The Big Bang singularity and the singularity inside a black hole may have something in common. They might be two examples of the same fundamental problem: our inability to describe extreme conditions with our current theories. Wherever we push physics to its limits, whether at the heart of a black hole or at the birth of the universe, we run into the same wall. What all this tells us is that while our equations can take us incredibly far, they cannot take us all the way. We can describe the expansion of space, the cooling of the early universe, the formation of particles and atoms, but only from a certain point onward. And that edge matters because it shapes the kinds of questions we can ask and the kinds of answers we can trust. If someone asks what happened a second before the Big Bang, the most honest answer we can give with our current physics is we don't know and maybe we can't know. This shows us how far we've come and where the next breakthroughs need to happen. For now though, we can only approach the beginning from one side. Like looking at the edge of a map and wondering what lies beyond, knowing we can't draw it until we invent a whole new kind of crafty. The end of time's arrow. How entropy, the end of time, behaves in reverse and eternal models. We remember the past, not the future. We grow older, not younger. Heat flows from hot objects to cold ones, but not the other way around. All these patterns follow what scientists call the arrow of time, a direction in which events unfold. At the heart of this idea is a law of physics that has never been broken. The second law of thermodynamics. It says that in any closed system, entropy, the amount of disorder, will tend to increase over time. In most of physics, the basic equations work the same way, whether time moves forward or backward. If you watch a video of two billiard balls colliding and then reverse it, the backward motion still looks like something the laws of physics allow. But if you watch a glass fall off a table and shatter, reversing that scene, watching shards fly up and form a perfect glass, feels wrong. That's entropy. It tells us that certain processes have a preferred direction. This one-way flow of entropy gives time its sense of direction. In our universe, as far back as we can trace, entropy has been increasing. The early universe was hot and dense, but it was also surprisingly uniform. That's actually a low entropy condition, even though it might not sound like it. As the universe expanded, matter clumped together into galaxies, stars, and planets. These structures added complexity and in the long run more disorder. Eventually stars will burn out, black holes will evaporate and the universe will become cold and dark, an end stage called heat death. That would be the maximum entropy state. But if entropy defines the direction of time, what happens if entropy starts decreasing? Could time itself reverse? In certain models of the universe, entropy might actually run in the opposite direction during different phases of cosmic evolution. And that opens up the possibility that the arrow of time as we know it could flip. Instead of imagining that everything started with a Big Bang and has been expanding ever since, we can ask what might happen if the universe were to stop expanding and begin shrinking. In standard cosmology, this could happen if gravity eventually overcomes the outward push of expansion. Space would begin to contract, galaxies would draw closer together, and the universe would collapse into a big crunch. In some versions of this idea, as the universe contracts, the entropy might not just continue to rise. Instead, the trend could reverse as matter gets squeezed back into a smaller and smaller volume. Some physicists argue that entropy could begin to decrease. That would mean the direction of time, at least as measured by entropy, would also flip. To observers inside that contracting universe, it would feel like time is still moving forward. But from the outside, it might look like time has begun to run backward. This kind of thinking has led to proposals in which the universe has two symmetric halves. An expanding half with increasing entropy, the one we live in, and a contracting half where entropy increases in the other direction. The two were connected at the point of lowest entropy, which would be the Big Bang. This doesn't mean time literally reverses in the way we experience it, but it means the thermodynamic arrow of time, the one linked to entropy, does. In one such model developed by Shaw Carroll and Jennifer Chen, the idea is that the universe can spontaneously generate patches of low-entropy space from a timeless background. These patches then evolve in both time directions away from the low-entropy state. Each side sees itself as having a forward arrow of time, and both consider the low-entropy point as the beginning. From their own internal viewpoint, each half of the universe sees time flowing outward from the middle. Another place where this idea shows up is in cyclic cosmologies. In these models, the universe doesn't have a single beginning or end. Instead, it goes through an endless series of expansions and contractions. After each big crunch, there's a new Big Bang. The cycle repeats, possibly forever. In these models, the universe resets itself with each bounce. The challenge is figuring out how entropy behaves through those cycles. If entropy keeps increasing with every cycle, it would eventually reach a maximum and the cycles would stop being meaningful. But if entropy can somehow reset, maybe through quantum effects or exotic physics, then the arrow of time could also reset. Each new cycle could start fresh with low entropy and a new direction for time. A more recent and technical version of this idea comes from the conformal cyclic cosmology proposed by Roger Penrose. He suggests that the distant future of one universe can be mathematically stretched and reshaped to look like the very beginning of the next. The idea relies on the fact that as the universe becomes cold and empty, all matter decays and only massless particles like photons remain. In such a state, the concept of time becomes meaningless because there are no clocks or changes left to measure. Penrose claims that this timeless state can then connect to a new Big Bang where time begins. Again, this idea might sound strange, but it's rooted in real mathematics. And it shows just how much our understanding of time depends on the presence of entropy. Without entropy, there's no direction. Without direction, there's no time as we know it. All these models share one idea in common. The direction of time might not be a fixed universal property. It might emerge only under certain conditions. Specifically, when entropy can increase. If those conditions change, so might time. This is very different from the everyday way we think about time as something absolute, always ticking forward no matter what. But in the world of cosmology, time is tied to the structure of the universe. And if that structure flips, bends, or repeats, then the flow of time might do the same. Of course, these are still ideas.